The birth of nanotechnology can arguably be traced back to December 29, 1959, when Nobel laureate Richard Feynman laid down the ultimate scientific challenge to a room full of colleagues: to control and build matter atom by atom. Though the ability to handle matter at this scale remains elusive, researchers are closer than ever to achieving it. This month's issue of MRS Bulletin showcases how scientists are using particle beams to meet Feynman's challenge and, in the process, revolutionizing how we view, understand, and build with atoms. In the decades following Feynman's lecture, researchers were making significant headway towards atomic-level control of matter, even if they could only see the building blocks themselves at the time. Using a narrow stream of electrons or ions, researchers could resolve individual atoms in a material. Advances in electron microscopy have now made high-resolution imaging of atomic systems routine. Along the way, scientists discovered that electron beams can often damage materials on the atomic level. It wasn't long before researchers suggested using their microscopes to add or subtract material at will. In effect, they turned what appeared to be an imaging problem, unintentional damage to a sample, into a way of sculpting microscopic objects. Today, advances in that direction have equipped researchers with the tools to do much more. They can now deposit atoms or atom clusters to form objects from the bottom up. They can repair the tiny circuit elements that will drive the next generation of computers. And they can track the movement of single atoms across the nano-landscapes of emerging materials like graphene. But before meeting Feynman's challenge, researchers will have to address a few others. One is control. While writing with particle beams has been proven, it isn't clear how the parameters can be tweaked to form different structures. Another is reproducibility. To manufacture on the atomic scale, researchers must make sense of the cascades of collisions generated when a beam interacts with a target material. While true atomic precision remains elusive, the gap is quickly narrowing. The approaches highlighted in this month's MRS Bulletin represent important advancements that could soon give researchers the level of control over matter once envisioned by Feynman.